Welcome to my talk on, my clicker doesn't work. There we go. It's just delayed. Welcome to my talk on Tacit DSLs. My clicker really doesn't work. There we go. So DSL is domain-specific language. We've had some experience with these in C++, right? We have, man, this thing really isn't working. Somebody else have a clicker?
This is that kind of conference. Everybody would just sit
A. Yeah, there we go. Okay. So this is next. Yes, we've got printf, which was obviously perfect, which we inherited from C, and then we added I/O streams, like the stream operator thingies to fix that, which obviously worked out perfectly. And then we have regex, which, thanks to Hannah, will be perfect at some point, right? It's yeah, we're fixing that, right? And so now we have we're getting a new one, right? The ranges DSL, and so the ranges DSL. Oh, come on in. I'm not sure if there's a place to say it, but come on in.
back of the bus.
So as you can see on his shirt, the ranges DSL, the concept is you have a range, you can pipe that into an algorithm that works on that range. Out of that comes another range, which can go through pipes, right? So ranges go through pipes, and you can concatenate them. And that's the whole sort of DSL part of the ranges, right? And we could have ranges without DSLs. That'd still be good, but we're probably adding another DSL to C++, right? So the question with our history of DSLs in C++, is this good, right? Is it good that we're adding another one, or are we going to just say, damn it, we have to fix it. We need another Hannah, right? Well, you're fixing one of them. Anyway, so there are several ways of thinking about this, right? I mean, sort of in the beginning of my career, I thought, well, is this good? Well, is this going to help me express myself in this use case? If yes, then yes, it's good, right? But sort of over the years, I've started thinking a little bit differently about this. So I'm going to try and, with this quote of somebody smarter than me, put you guys in sort of the same mindset that I want to think about these things in, right? And some of you are going to remember this, recognize this quote, right? Conventional programming languages are growing ever more enormous, but not stronger. Inherent defects at the most basic level cause them to be both fat and weak, right? Their primitive word-at-a-time style of programming inherited from their common ancestor, the von Neumann computer, then you flame, a couple more inherent defects, and their lack of useful mathematical properties for reasoning about programs, right? So you blasting, C++ among other things, right? So this reads like a YouTube comment, right? But it's it's actually John Bacchus before I was born, right? At his Turing Award ceremony. It was a Turing Award speech, and got the Turing Award for Fortran, right? And so this is obviously somebody smarter than me. It is Turing Award speech, railing against word-at-a-time style, programming languages, which is, Fortran is a word-at-a-time. So he's railing against his own creation at the Turing Award ceremony that he got for that creation, right? So there's kind of something here, right? And sort of the alternative that he was pushing was functional programming. Right? So I've seen this with my friends too, this kind of behavior where as soon as they start dabbling in functional programming, they don't really come back, right? And the reason for this is obviously that the functional programming community have some really hard drugs. No, but there's something very powerful in being able to compose basic blocks into larger things, and then being able to compose those into larger things, and then just build the world out of pieces, right? You have to start with the right pieces and the right concepts of composition, but it is very, very powerful and apparently very addictive. I I actually, like, you know how people don't get addicted to things that are just terrible? Like there's some like Indian drugs that are just so painful that people like try them and then don't get addicted. And the only functional programming language I'm proficient in so far is template metaprogramming. So,
So you built up an
yeah. So but like sort of looking back at this, the ranges DSL is not necessarily new, right? It's essentially, you know, pipes and shell, right? And this is also older than me, and it's, you know, compositional. I can take, you know, a list of the directory and pipe it into an algorithm, which just, you know, lops off the first three, lops off the back one. I can chain them, you know, same sort of a concept, right? Huh? Yeah. So this is not a new DSL, and it's kind of proven itself, and it should be familiar to most people, right? And so yes, this is probably a good thing, right? It's, you know, generic, composable. It allows me to express myself in sort of a higher level, or sort of declarative composition, rather than, you know, the what, not the how, of dealing with ranges. And then there's sort of this second influence on sort of my opinion on this, which is actually very similar. And this is a Sean Parent talk from more than 10 years ago. It was a Google Tech talk. It's not actually a conference talk. He should give it, like, if you ever asked to warm up a talk, this is the talk. Hi, Sean. It's called A Possible Future of Software Development. And in this talk, he covers a lot of ground, right? But the thing, you know, one of the first takeaways is, if you want to understand your program, make a directionally annotated graph of where the data flows, right? And if that's a terrible rat's nest, then there's your problem, right? Because if you can't reason about where the data flows, you can't reason about your program, right? And this is probably one of the pieces of advice that has influenced my style of programming the most. And together with some other people, he built this. You know, this is sort of the second half of the talk. He built this model for modeling GUIs, right? You know, graphical user interfaces at Adobe, and forced all the other engineers to express themselves in a declarative DSL. You know, they're not programming against the abstract machine or the concrete machine. They're programming against a model which he built specifically for this purpose, right? At a very, very high level. And this is actually, to a certain extent, more powerful than Bacchus, because he actually has proof that this was a good idea, right? He shows sort of bug tracker and percentage of bug tracker that is GUI bugs, right? And it goes from, you know, quoting from memory, something like 35% down to essentially 0, right? Large organization, many, many, many engineers, same people, just forced to program in a different paradigm, and bugs went down substantially, right? Yes, Marshall.
Just that. This was the BoostCon 2007 keynote, by the way. This one.
Oh, yeah. Is that not on video?
Pretty sure it is, but it'd take me a while to find it.
Okay, Marshall's comment was it was the BoostCon 2007 keynote. Yes. So, okay, if that's on video, then yeah. So I mean, I work on microcontrollers. Microcontrollers are dirty, right? You know, you have to worry about things like the time domain, and like, how do I even express myself in the time domain in Haskell, right? That's just not a thing, right? And I've said this before, and somebody came up to me, he's like, oh no, we can program microcontrollers in Haskell and just use this framework. And what this framework does is actually kind of awesome. But what this framework does is it's basically a Haskell program that generates C code and then compiles it, right? So my world is too dirty for, you know, programming in Haskell, at least without a whole lot of work. Right? My domain's too dirty to program in C++ the whole time, right? I mean, I have to go all the way down to assembler and crap, right? But at least at a high level, can I model my programs? Can I write my programs the same way I want to think about my programs, as a directionally annotated graph of data flow, right? So, you know, this is somewhat domain specific, right? You know, the CAN bus is, you know, some data bus that connects modules in a car together, or robots on an assembly line or whatever. And it has like packets up to 8 bytes. And so if you want to send larger packets, you need some transport protocol, which like stitches together a bunch of single packets, and then does things like functional addressing and blah, blah, blah. And then once you're done with that and you say, okay, this is a packet for me, here's the payload. Hey, upstream guy, you know how to deal with this. I don't know how to deal with this. Can I write this in the ranges DSL? Well, not really, because I'm kind of lying to myself. Because if there's an error, then I have to be able to send again, and the protocol sometimes like gives up on whole strings of packets. Like, okay, well that's too many errors. Send the whole thing to me again. And so I need like a buffer to like buffer all the intermediate packets, so I'm sure that this is a full transfer. And then that goes into, well, okay, no, I can't do this in ranges, right? What about something a little more simple, right? Maybe I'm a smart light bulb and I don't do error handling because I'm in the Internet of Things and they don't do error handling, right? So, so people send me JSON packets over like MQTT is like this machine-to-machine protocol. And so I have like several layers of protocol that I'm kind of ripping off, receiving data. And at some point, I'm either going to turn the light on or off, or I'm going to change the duty cycle as in dim it, right? So I took out error handling. Can I express this in the ranges DSL? Well, it's hard because I got this fork at the end, right? The ranges DSL is a pull model, right? Pull model means I have a bunch of composed algorithms, and I ask the first one. It says, well, I'm a transform. I don't know, I can't give you the next thing, but I know how to modify it. But I know my upstream, so I'm going to ask it for the next iterator, the next object, right? And it's like, well, I'm a filter, so I'm going to ask my upstream. Oh, no, that doesn't fulfill this predicate. OK, upstream, give me another one. Well, that doesn't fulfill it. OK, upstream, give me another one. OK, that fulfills it. Here, downstream guy, right? So we're basically iterating over the range. We're pulling values out of this chain, right? And at some point on the other end of the chain, there's a container that has all the values. And we're pulling them through the chain. This is called pull model, right? And there are like several other languages that are implementing pull models now, right? You got Rust iterators and a bunch of other stuff. It's kind of like the zeitgeist, right? This is what we're doing in programming languages right now. But I actually have a push model, right? Like I am an interrupt service routine of this serial port. I have a byte. Hey, here's my byte. Do something with it, right? So we don't really have a domain-specific language for composing functions in a push model paradigm, right? I mean, we do program in push models. Just channeling my inner Sean Perrin, I'm going to call these incidental push models, right? I mean, we're a function call. Somebody pushed something into us, right? They called our function with a parameter. We've got that parameter. We do some kind of transform on this parameter, whatever that transform is, doesn't matter. And then we call the next function with whatever came out of that operation, right? We're pushing stuff into it, right? And then maybe we're out of that operation comes maybe a Boolean and some data. And then we're pushing it into one of two functions, right? We're forking, if you will, right? We're saying, okay, if this predicate holds, then that function gets called with this. And if this predicate holds, then that function gets called with this. And this could be like arbitrarily complicated. There could be a whole like state machine here. We could be like a member function, or this state machine could be a global, or I don't care. We could be a coroutine for all I care. Somehow this state is like surviving multiple calls to ours, right? Maybe we're, saving up a bunch of bytes being pushed to us, and then once they make sense, then we'll push it as a whole packet to some function, right? Yes?
So can you clarify a little bit here? Because I've actually always thought the opposite. I've always thought of ranges as a push model until you actually use it in a loop, and that just happens to be exiting the ranges model.
Well, it's a lazy push model, if you will.
Yeah, exactly.
Right? But once you actually start to use it.
But then you exited their model, right? Because then you're just using regular C++.
Yeah, okay, but let's see. Another way to phrase this. I mean, it is a good comment. Like, another way to phrase this, when you work on them, you work on them in a pull context. Is that a better phrasing?
But when you compose them, you compose them by push.
I have to make a self-plug. Search for the pipes and filters architectural pattern in pattern-oriented software architecture volume 1, where actually it's explained you have a pipeline, pipes and filters, and you can implement the step between the filters, either push or pull, and within a pipe, and you can have both ways to do that.
Yeah, I mean, that's one of the reasons why I'm doing this talk, right? I'm presenting a bunch of stuff that I'm not necessarily sure about and soliciting feedback, right? I mean, the sort of the meta of this talk is I'm trying to unify a bunch of different DSLs in one DSL to rule them all, and it's going to be wrong, and right? So I need something that I can use in a push context to rephrase that, right? So if there's a state machine in here, right, then this if, I mean, this might be, are you in one of like these 5 states, kind of an if, right? And so this if might actually be strewn across several transitions, right? I mean, I'm kind of, conceptually the data is all going down this sort of this arrow in my DAG, right? But like in code, it's scattered all over these different routes that it can go through my program, right? And if I want to like change this to where after we get out of JSON we're pushing to a queue and then somewhere else we're pulling from that queue, right? Then I'm going to refactor a whole bunch of code, right? Because it's all kind of hardwired, and I'd like to do that differently. So if I were just to say hypothetically be able to compose functions, and this is looking a lot, I mean, who was at Michael's talk yesterday? Okay, some people. This is going to actually, by chance, look very, very similar. Like, we didn't really coordinate on this, and we came up with a very similar syntax. We got some input. He called it in. I called it input. We pipe it into, functions, and they return, and that return gets piped in the next function. Right? So conceptually, we're, calling fun with 2 parameters, because that happens to be what input is. That's returning 3. We're piping it into Gun, and that returns 6. We're piping it into... And these are actually Alex Andrescu's function names, so complain to him. And that returns void because it, I don't know, pushed to global state, or fun is some stateful functor that's pushing it to somewhere else, or I don't care, right? But what if fun returns a tuple? Fun returns multiple things, right? I mean, this will work in the incidental push model quite well because, well, I'm in a function, I got a couple of local variables, I'm going to call a function with those local variables because they dropped out of the transform I did on my input, and it all works, right? Well, the return path, you only have one thing, right? So you have to wrap them up in a tuple or similar, right? And then, unwrap them, right? So if we have, so if we have, some composition of things, right? Well, the function call operators of all these things, or the functions themselves with their free functions, they could all be templated, and we could do sort of fusion metaprogrammy kinds of operations on these things, right? So we look at sort of HANA, which is current gold standard in this domain, right? We have a tuple of 3 different kinds of things. We have a generic lambda, which is sort of operation that can act on all 3 of these things because it's function call operator is a template, right? So as long as all 3 of these things have a member function called name, right? And this is just the beginning of the HANA tutorial, right? I can do a HANA transform on tuple of animals and this functor, right? This generic lambda, and it's going to spit me out a tuple of string, 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 because that's the type of the names, right? Or maybe string, string, string view, if one of them is like a string view, right? Whatever the type that came out of that lambda is, that's what's in the returning tuple. And I can compose these things pretty well because they take tuples and return tuples. So if I want to reverse this, I can just say, hey, reverse whatever came out of that, right? And if I want to express this in sort of a ranges DSLE kind of way, I can say, okay, I've got a tuple of animals. I'm piping that into a transform with this predicate, and then I'm piping that into a reverse, right? It's the same thing, just, inside out, if you will. What is the type of the thing that is going through that pipe?
Neebloid.
Neebloid. Well, the operations are probably neebloids, but the type of that thing is unobservable. Library implementation detail, because yeah. So with HANA, where we can't look ahead in transform and say, oh, the next thing is a reverse. We have to return a tuple with like encapsulation and a public interface and all that stuff. And that costs us at compile time, right? But here, transform can look ahead and say, oh, the next thing's a reverse. Well, I'm just going to give it some thing that publicly derives from all the pieces, and then you can just cast rather than indexing and all these dirty tricks because nobody can actually touch it, right? It's within the DSL. I can also do a bunch of other stuff. But sort of that's last year's talk, or at least what last year's talk should have been. It was a little before its time, and I came off as a crazy professor, and yeah. You know, we can write sort of a fusion metaprogramming library that looks a lot like ranges, right? If we have this concept of a pack of things can go through a pipe, and not just a range can go through a pipe, right? And it's a little flawed. We'll get to this in a minute, right? But okay. So the concept of this thing that can go through pipes now is some library defined type that's unobservable, but conceptually this is just a parameter pack, right? You know, product type, meaning it's the sum of all states that it can be in is the product of all the states that the aggregates can be in, right? So if I have a pack of, I don't know, unsigned and bool, well, that's max int of unsigned plus 2 times 2, right? So I'd like to be able to just do this, right? But I can't because A is an unexpanded pack, right? But I can just make a factory function that'll just turn that into this, implementation defined type, and then it can go through pipes, right? But I still have another problem, because I mean, what are foo and bar, right? Well, foo and bar are nibloids, or foo and bar are some kind of functor or something, then this will work. But if they're free, if they're free functions, it'll also work as long as there's just one of them, right? If it's an overload set, which it probably should be because we're in a template-y generic context, that's not going to work because you can't like capture an overload set as a function reference. And this is a bug in the language that a lot of people are running into in all sorts of places and have run into in the past. And there's like, oops, getting ahead of my slides. There's a paper on like how to fix it, and there's been a bunch of other papers that have failed, sadly. This one might succeed, I hope so. If it doesn't, well, we can just make a macro that just puts a lambda around it, and then it works again, right? Except for older versions of the language where lambdas can't be const-expr, and it's just a can of worms. But for the sake of this talk, we're going to assume that this problem has been fixed, right? Just to save space on slides. There are workarounds, right? Also, a problem with all DSLs is when you stop being lazy, right? So the pipe operator resolves from left to right. So we got pack and transform. Well, we don't want to act on that yet because we want to be lazy, right? So we're just going to make like an AST node of this was on the left-hand side, this was on the right-hand side, and it was a pipe operator. And then the AST node is going to be on the left-hand side of the next pipe operator, and then accumulates on the right-hand side. So now I just have a bunch of like lazy AST that hasn't done anything yet, right? And it used to be that this kind of worked because at some point it would have to be converted to some type, right? Before we had auto. And this only almost always worked, the conversion operator trick, because, well, what if you passed it to a function template? Well, then that wouldn't be evaluated there because the function template would match this ugly bunch of AST, and then it would get evaluated in the function where somebody actually had, and that might be later than you expected, so you may have bound something by reference and then it was out of scope and whatnot, right? So lazy evaluated domain-specific languages have been hard to do correctly in C++ forever, basically, right? There is a proposal for operator auto, which is basically, is somebody like deducing this type? If yes, you can do a conversion if you want, right? To try and fix this problem, but it doesn't quite fix the problem because you still have the function template problem that you had since the beginning of time, right? So we could, like force a return type, but then user would have to do that, and that would be stupid. Or we could like say, okay, well, mine's left to right. As soon as you see, some special tag at EK. Yes, Bryce.
Operator auto is also already a thing.
It's already a thing.
It already has a meaning.
Oh, yeah, okay.
Yeah.
So So it's stupid for multiple reasons. Anyway. So the timer died, but yeah. Yeah, question? What? Who? Sorry. Yeah. Okay, so DK or done or go gadget or whatever you want to call this thing, or eval, or right? But that's ugly. So we could take a later binding operator that binds from right to left, and then as soon as you see the thing on the left that's not a callable or a, whatever, because the input's, going to be a pack of some kind, right? Then you can evaluate eagerly because okay, I'm the last binding operator and I go from right to left, so I must be the end of the chain, right? And this actually helps us for another reason with an ambiguity, right? So if I have a tuple and I want to, right shift operator that thing into a callable, well, that's apply, right? Because it works in a DSL rather than it being a free function, I can say, okay, well, what if I have this composition and foo returns a tuple here, right? Return type of foo is t, right? And so which overload of bar do I mean? Do I mean the one that takes a tuple of int and bool, or do I mean the one that takes an int and a bool? Right? It's ambiguous. So if I say, okay, pipe just means whatever you got in, just forward it through, and right shift equals means unwrap that thing, take the wrapper away, and here's the internals, then I can resolve that ambiguity, right? So I can say pack, okay, that returns a wrapped something of implementation specified type, and if you use this operator, then it'll unwrap it. So unwrapping things is the only way to get something into this DSL, right? So this becomes somewhat pure, right? We can actually make it so nobody can actually ever see this type, and that means we can optimize the hell out of it, right? So, correcting the previous example, we'd have to unwrap animals, right? And then that would work again, right? But what does it mean to unwrap an optional, right? If a tuple is a wrapper around a pack of things, well, an optional is a wrapper around either nothing or that thing, right? And so if we unwrap it, well, you can't call a function with nothing because I just made up what nothing means, right? So you can't call, if you want to call a function without parameters, that's calling it with an empty pack, right? That's different from nothing. You can't call a function with nothing, right? So we can just skip the function call if we have nothing. And so what do we decay to, right? Because that pack type, that's our internal type. It's got to decay to something at the end. So, well, what is in the pack? Well, it's a sum type of either nothing or a horse. So that's an optional horse. That's what we're going to decay to. And then you can specify what you want to decay to if you want. Just pipe it into something and then, right? So if I have a horse and I want to add magic to this horse, right? And then I want to add a horn to this horse, right? Then, okay, that'll work, right? If I didn't have a horse, then unwrapping the optional, like if the optional didn't have anything in it, then I'm going to skip add magic and I'm going to skip add horn because I still have nothing, right? And I could put in like an or else, which was then matched to having nothing coming down the pipe, and otherwise would just forward everything through to the next thing, right? But what if not all horses can be magic? I mean, this is my gut feeling that some horses can be magic, but not all horses can be magic, right? So that could fail, right? So add magic, well, that's going to be taking a horse and returning an optional of magic horse, right? And so we need to unwrap that one again. So it doesn't really matter where we get a nothing. As soon as we have one, it'll just propagate to the end, and our end result will be an optional of either unicorn or nothing, right? And so we basically just reinvented Swift's dot question mark operator, right? I'm trying really hard not to say monad. Yeah, no one's ever used this to mean anything similar to this before in history, right? It wasn't just like randomly in cocaine on one of my slides. But so there's a lot of sort of noise compared to the signal here, right? You know, the thing that we're doing is we're adding magic to something, whatever it is that's coming in. And you know, if it's not, okay, maybe it's not an optional horse. Maybe it's I don't know, an any that could be a horse or something else. Yes?
So what was your problem with having a done stage of the pipeline?
It's verbose.
So it's interesting because that's the exact solution that Eric's come up with for asynchronous ranges.
Yeah.
In 1055 and 1194.
Yeah.
So.
I should be following that. I suspect we're going to have some overlap. I've talked to him about this a little bit, but just a little bit. So, yeah. Apparently I should have been talking to a lot more people, including Michael and Eric and all the other people that are like, we'll get to a bunch of stuff that I'm apparently reinventing from other people too. Yeah, yeah. So we're basically, this is the signal, right? The rest is just fluff, right? So you know, but we still need to unwrap the thing coming in, right? So can't we just say, okay, if you have a fragment of AST, that always has a function call operator, right? So this is a call. Any fragment of AST in this DSL is callable, and when you call it, that's just putting a pack in it, right? Because it's a variadic function call operator, right? But if we're expecting an optional horse, right, we need to unwrap that thing, and this operator is set, unwrap and pipe into the next thing at the same time. So okay, we have this identity that just forwards all of its stuff, and then we can have the unwrapping, or we could say, well, there's like a prefix unwrap operator. Look, there's a wrapping paper flying away, right? And this is not really as dangerous as it seems, because I don't think there's a whole lot of overlap between bitwise not and callable things, right? So this will probably work, and this is just syntactic sugar, right? Like the message is sort of the core. So now I have something that's a little more generic than the upper case, right? I can take anything that's unwrappable, and then the add magic, well, that's going to take a horse. So after you unwrap it, it has to be a horse, right? Otherwise, you'll get an error message. It's actually probably not going to be too bad, right? You could say, okay, add magic doesn't take this thing that's not a horse, right? So I've got sort of this terse, terser lambda syntax, right? So I can just, call this thing like it normally calls something, and, foo has to be something unwrappable and whatnot, right? So if I've got this terser lambda syntax, just as kind of a sidestep, I have this Fusion metaprogramming library. It's got a concept of a T. So I'm going to introduce concepts here, right? So T is also a thing from shell, right? A T is like a T fitting in a pipe, right? So I've got this pipe, and then it's T fitting, and now it's two pipes, right? Or it's a variadic pack of T fittings that is N pipes, right? And these pipes don't obey the laws of physics because all of the input parameters go out all of the pipes, right? So this is a little bit different than T on bash, but right, okay, so I have three, callable somethings, and I'm forwarding all parameters into all three of them. And the output of this is a pack of three things, which happen to be, image, width, height, right? So I can, I can write these get image, get width, get height. Maybe I'm capturing name parameters. Maybe I'm doing some, fancy deducing defaults, right? Maybe I don't have a width, but I can deduce the default because I have a height and an aspect ratio, right? So I can come up with all sort of Fusion metaprogramming rules to figure these things out, right? The point is, like, this is one line of code, right? I mean, this is how you'd write the function otherwise. This is how you'd write the function with, fancy parameter-y stuff. And so we've basically replaced boost parameter with a more powerful thing in one line of code because this composes well, right? This is going to become a recurring theme. But, we were looking at sort of this optional thingy. There's a paper from Simon Brand, which is a very well done paper. He's got a reference implementation and everything. I even used some of his code from his reference implementation of an optional with an extension. I'm not saying monadic. And this is sort of the use case that he presents in his paper. He's got this cat and he wants to make it cute, and so he has all these operations to make this image view into a cute cat, and each one of them can fail. Almost all of them can fail. Resizing can't fail, so down at the bottom, make smaller. Can't fail, but this is sort of his, okay, this is how you'd write it today, and this is how he proposes to write it. I think the newest proposal, it's not map anymore, it's called transform, but, right, so this is basically this, right? We didn't actually try to write a monadic optional, it just kind of comes out in the wash, right? But is optional the only sum type? Not really. I mean, if you really think about it in the right way, a lot of things are sum types, right? So, optionals may be a variant of nothing or thing, right? And so, what is unwrapping a variant and then calling a function with that unwrapped sum? Well, that's visit, right? We can actually make it in a much more powerful visit, but just for all intents and purposes, this is visiting the optional, because you took the wrapper away, so now it's either this or that or that or that, right? You have, you can have some types in these pipes because I just made up what they mean, right? So this is kind of the part in the talk where I've implemented this far in sort of, relatively, and this, you can do a bunch of other, fancy stuff, and this actually ends up being a little more performant than standard visit. But, okay, can you visit on like an unwrapped pointer to int? Is a pointer to int some type? Well, kind of. It's either nothing or it's an int, right? Is it null pointer? It's nothing, right? So I wrote this super tersely because I'm sure there's some people here that want to see things super terse, right? We could have taken like the left, like round parameters, like these guys, and made that into a named AST fragment, right? So we've got this new thing coming in here called use, right? And a use is basically standard bind on steroids, right? And don't get hung up on the name, right? I'm terrible at naming things. It's probably going to get renamed at some point. But the idea is you can use placeholders like you can in bind, right? You don't have to put the thing you're binding to in the parameters because it's on the other side of the pipe, right? And so we're saying, okay, parameter index 1, let's unwrap that and then put it into the pipe, right? So that's what this use is, and we're piping that into Baz. Baz is some callable, right? And on the right-hand side, we're just calling this AST fragment that we created with our pointer to int, right? And so, yes?
Would that require the pipe would actually fail if you have null pointer?
Well, we could define what unwrapping a pointer means, right? Because this is our unwrap operator, right? And so we could say, okay, a pointer turns into a some type of, the thing pointed to or nothing. And then if it's a nothing, well, then we don't go through that pipe. We just forward the nothing on down the chain.
Unwrapping already happens with the tilde.
Yes. Yes. You see the wrapping paper, man. It's obvious, right? Yeah.
Why not bar pipe into that? Why are you all of a sudden using explicit function calls instead of?
No apparent reason, just because I can, right? You'd have to say pack of bar into that, right? Because bar is a variable. It's not a pack of one thing in the pack variable, right? And variables can't go through pipes because otherwise we'd have ambiguities, right? So packs go through pipes, right? But with the function call operator, you can like get around that. Right? So not only product types, but some types can go through pipes, right? We have unwrapping, and we have two new things that can go through pipes. And that's basically the end of the extensions to the ranges DSL, and we're going to have fun with it now, right? So I've had this problem where I have like two objects that consume events, right? There's some, encapsulated module thingies from, and I have this project where they both exist, and they're both pulling from the same event queue. You want to use the same event queue because then you have like sequential consistency, which order they get pushed in is, retained. But now I have this variant of, the sum of all those two kinds, those two sets of events, and I want to visit on this variant, and like I have a list of which sets of events this is, right? But I have to do a bunch of metaprogramming to make a new visitor that will visit on this variant and then call like two different visitors depending on which subset of this variant is currently in the variant, right? But we have this Fusion metaprogramming library. So what does it mean to partition an unwrapped sum type, right? Well, you got a bunch of options, and in template metaprogramming, you can just say, well, the ones that fulfill this predicate, they're going into that visitor, and the ones that don't fulfill the predicate, they're going into that visitor, right? Like, this is perfectly implementable, right? And if I can partition, well, I can also filter, and if I can filter, well, that's basically just a subset of all the things that could possibly be. Maybe I know that it can't be these like 10 things, it's just one of these 3, right? Or I could just explicitly say subset. Well, if I explicitly say subset, then V doesn't have to be a variant anymore. It doesn't even have to be a closed sum type. It can be an open sum type, like an any, or a pointer to a class in hierarchy, right? So rather than having these chains of if dynamic cast of this succeeds, then you're this. If dynamic cast of this succeeds, or substitute any cast for the any case, right? And we have these open sum types, meaning the user can extend what kinds of things can be in here. I don't know all the things that can be in here. I can just say, are you this thing? No, okay, are you this thing? Super verbose and error prone and whatnot, right? So I can say, well, I would just want this subset because these are the ones I care about. And then I'm going to visit over that subset, right? I mean, it's not going to be as performant as visit because I still have to like linearly go through them and say, are you this thing, are you that? But I can do that under the hood, and maybe optimizers understand me better, right? So maybe it might be more performant, but it's definitely sort of clearer, right? But yes.
Just to understand that, what that line means is if the thing that you're putting in is either a T or a U.
Yes.
Forward it to bar, and you will have 2 bars, one for T
yeah,
and one for U.
Exactly.
If it's something else, then nothing.
Then it's nothing, and then it goes. So the return of this is going to be some kind of optional, right? So if I can filter, then I can just do like a match, right? Because this is just filtering on are you this thing, are you this subset, or this, right? And okay, this is a little clever, but this is obviously C++ now, so this is crazy shit. We don't obviously have an equals bracket operator, right? So what this macro case is doing, case underscore, it's constructing a class with a template parameter, hack helper or whatever class with a template parameter int, and it's taking the address of its copy assignment operator, but leaving off the equals, right? And so we're swallowing that equals and returning a function pointer, and then I can overload angle brackety on hack helper, and then pattern match against that thing to get the int back out. I don't care about the rest. And then, right? So yeah, I mean, probably don't do this in practice, but this is what this conference is for, right? Here we have another sort of case of use, right? I'm just binding extra parameters onto it, because if it's not a placeholder, then obviously it's a bound something, right? But this is what I really want to do. I mean, this do in practice, right? I have a bunch of different things that consume events, and rather than breaking encapsulation of like, I consume these kinds of events, so you better like program this into your event dispatcher tree that these go to me, right? I mean, I haven't really seen a lot of like pretty event dispatcher code, because it's got to be like lightning fast, but it's like implementation details of all the things you're dispatching events to, right? So if I say, okay, anything I dispatch events to in sort of my library world has to have this member function dispatch, which is an AST fragment that matches and then pipes through things. Well, then that's in that class encapsulated, and I'm just composing them all, right? So this is something I'm certainly going to use in practice, right? And so can I write this now? Well, yeah, right? I could probably write this, right? But I've been lying to myself, because even if I don't care about errors, I mean, if I have an error in the JSON in like the third letter, I still want to like, count angly brackets and go to the end, or the MQTT packet, maybe I want to look for the terminator thing at the end, right? So I want to just swallow bytes until I'm there, or otherwise one error is going to lead to a bazillion errors, right? So I need a state machine. Plus, like MQTT and JSON are also state machines, so it'd be nice to be able to make state machines, right? So So like, let's get into sort of our generic-y thinking about the world mode and say, what is a state machine? Well, it's a sum type, right, of all the states, right? So if it's a sum type of all the states, then I can just steal syntax from Hannah to represent transitions. Well, that's just a function, right? Like, you know, okay, you got state, got event, it's going to return state to transition to, right? Except mine have bodies because you probably actually want to do something in the transition, right? So, you know, how am I going to actually make this work, right? You know, the thing that comes out the other end has got to go back into the state machine, right? So use, okay, maybe I just made this so I have to swizzle them just so that I can show you I can swizzle them, right? You know, the process event down at the bottom there is taking the event as the first parameter and state machine as the second parameter. Here I'm swizzling them and unpacking the state machine because it's variant, right? And transition, okay, now this is visiting on, wait a minute, Cartesian product of unwrapped state machine and just this fixed parameter. Well, I always seem to want to do this in visitation, right? I want like the variant and then some other parameters. And now that I can disambiguate what I want, I mean, for all I care, the event could also be a variant. We're not unwrapping it, so it's just going through as one thing, right? So Cartesian product of, you know, array of things, you know, the variant and then one thing, right? Or if the event was coming off of some event queue and was already a variant, then I could just unwrap the second one too and just do a normal like Cartesian product of both of them and it would be the same result. Yes?
What's the difference between unwrapping into assign to and piping into assign to as you're done?
That's a good.
Like done to me.
Well, okay. So I'm going to ask a different question. You know, why don't we just put the assign to like on the other side of some equals thing, right? Like, you know, okay, not make this a nebloid, make this like a lambda, and then have it give it a body, and say on the well, okay. Next slide. We might not want to transition, right? So if we don't want to transition, we don't want to assign a new thing to the variant. So in this case, well, one of them returned nothing while we're visiting over something that's got a nothing in it. In the nothing case, we're just going to skip the rest, and the state will just remain the old state, right? So this is actually pretty intuitive. And like from my experience, why do people like not write state machines? Well, because it started as an if-else, and then it turned into an if-else, right? And both of those things were easier than writing a whole state machine. And then, okay, well now there's like 5 cases, and that'd be a whole lot of refactoring. So I'm just going to add another one, right? So you need like writing the original if-else. You need that to be similarly easy as creating a whole new state machine, right? That's one observation about state machines that I have, right? And okay, well, so this statement, let's make it, let's say we have a guard, right? Well, I mean, you could either have like a guard or just an if within your state machine and then return some sum type, right? Now this fragment is another thing I made up, right? This is a sum type. It's a fragment of a larger sum type. We don't know which one, but if you ever put this in a larger sum type, it's just going to expand into that, right? So it's not going to be some type of S2, S3 nothing or fragment of S1 nothing. It's going to be some type of S2, S3 nothing, S1, oh, we already have a nothing. Well, that just collapses in, right? It's sort of, unpacked into, right? Or, just kind of, yeah. So, on sort of a side note, this is a lot more optimizable than if you had written this in sort of current way, because we're already doing a Cartesian product in transition, and we know that that's going into a variant and then being visited on again immediately, right? So we can just slurp that up into the, the first Cartesian product, and don't even have to create this intermediate variant. We're just creating it because we might want, for sake of thinking about it, right? You can optimize this DSL. And I forgot to mention this. This is another thing that bugs me on visit. You visit over this overload set that, I'd like to return different things and just get a variant back, right? But the standard library does common type. But if I model this so that I get a variant back, and then just pipe that into some operation that gives me a common type of that, right? And I can just slurp that up and do the same thing, right? So if you want that, you can still have that for the same performance. But if you don't want that, you want it to still maintain, continue to be a sum type, then, pipe through pipes, then you can do that too, right? So, depending on which state I'm in, I'm going to call these functions. Most of them will just blindly transition to something else, maybe do some work inside, right? And, if I'm in state 2 and event 1 gets called, then I'm going to do nothing, probably just drop that event on the floor or whatever, right? Or so on forward. Okay, make it like a full state machine, right? So this is like a state machine of size that is probably already useful, and it fits on a slide, including the framework implementation, right? So this is essentially Boost MSM on a line. Well, I had to break it because it's a slide, but right? There are some things that this can't do, which Boost MSM can, but that works both ways, right? State local storage is a lot easier in this model, right? Like, how do you initialize state local storage in the next state in MSM? Like, okay, read the manual, like, if you want to transport state out of the last state into the next state, well, I don't know, put some space in your event where you move it in there and then back out, and it's just pulling teeth, right? Whereas here, well, how do I put stuff, and how do I do like an on entry of the next state and put data in it? Well, I'd call a damn constructor. That's just intuitive, right? How do I move things from the old state to the new state? Well, I've got them both. They live at the same time, which means that this state machine is a little different than other state machines because on exit happens after on entry of the next state, right? And if you look at the object modeling group, they've left this like ambiguous on purpose, or not ambiguous, but undefined on purpose, right? This is somewhat allowed. It's different than most people do it, but if you're handling a lot of state local storage, this is kind of a godsend that they overlap temporally, right? And I'm handling a lot of state local storage in my domain because I don't want to have a heap. I want to put everything that's got an object lifetime that's not forever and not stack into state local storage because then everything's super deterministic, right? So I want to be able to handle state local storage very efficiently, right? So if I can do all this in 1 line, what can I do in 5 lines? So okay, this is getting into a little more sort of ninja-y stuff, right? So we're still using use, right? And we're taking, still taking parameter 2 and unwrapping it, still taking parameter 1, okay, that's the event, right? Forwarding that through, right? And then we're piping parameter 2 into this named tap, right? Well, what's a named tap? Well, that's a named tap, right? It's this way to get something out of one pipe and maybe put it into that same pipe or another pipe like down the road, right? It's got a name. In the pipe, there's a pack of things which are, positional, right? And then, maybe this has to do with me living in an area where there's a bunch of crumbling industrial infrastructure, but the way I think about that, you never just see one pipe. You see one like big pipe, and then you see a bunch of little pipes for all the like name stuff that goes along with it, right? So we're piping, _2 into a named tap or some like extra pipe that goes along. And then we can just pull it back out when we need it later, right? This is all implementable within this DSL, right? We have one tuple of things positionally going through pipe. And then we have another tuple of just named stuff that you can just pull out if you happen to have used that name, right? And so, in our process event thingy, we got the visitor, we got the state machine. So this is just another way of writing the process EV that we had before, right? Just now you can specify what state machine is and what the transition visitor is. That used to be hard-coded, right? And we can refactor all of the transitions into like, local functions in a class. I mean, they probably should be static, I'm noticing, right? They don't really need the this pointer, right? And visit should also work on overload sets of static things, right? Well, I guess no, they couldn't be a function call operator without. Yeah, okay, never mind. That's stupid. Anyway, sorry about that. So we have our state machine as like a private local thingy, and then we have all our transitions also local, and we have to be friend of process of E so they can actually reach our function call operators. And then somebody from the outside, like our public interface from the outside, is you just give us events, and then we'll just handle those internally, right? So we're doing some good refactoring here. Same kind of a thing, right? What if I want a submachine, right? What if I want a hierarchical state machine, right? Well, one of those states could just be another state machine, which is another sum type, right? And then every time I have this, I'm going to have the same pattern again and again, where the transition on, when I'm in that state, as in when I'm in that submachine, is just going to be forwarding events to the submachine, right? So because I'm going to have this thing again and again and again, why don't I factor this into some CRTP base class, right? So now we don't rely on the process event anymore. And we don't even have to say, here's our event handler, because every state machine is going to have an event handler, so we'll just put it in the base, right? So we're deriving public key from this base, so its public member function is going to bubble up. So I can dispatch events to this thing, right? And it's going to dispatch these events to my local function call operators, right? Which are my transitions, unless that transition doesn't exist, in which case the base has a fallback default, which is just going to assume that this is a submachine. If it's not, you're going to get a compilation error, right? So the default is to forward events to the submachine if that state happens to be a submachine. Right? But how do we get stuff back out of the submachine, right? How does the submachine tell the supermachine, hey, you need a transition, right? Well, I could make some transition have some, be some state that is not part of my state machine, right? And if I transition to something that's not part of my state machine, well, that needs to bubble up to the supermachine, and it's probably a transition in his state machine. Or maybe it needs to bubble up further, right? You can just arbitrarily nest these things all the way down, right? So we need to find some way of deciding, well, is this a transition to something in my submachine, or is this a transition to something in a supermachine that I need to bubble up? Well, we have this Fusion metaprogramming library, right? So this is our implementation of process event. Let's add a partition, right? We're going to need some predicate to say, well, are you part of my variant or not? And I've just deferred that to magic, right? But it's not necessarily hard to write, right? Just pack expand the types in the event and decide whether it's one of them, and probably uncv ref it all and whatever, right? So if it is some alternative of my local state machines types, well, then I'm going to assign to the state machine, right? And otherwise, I'm just going to return it, right? Identity just returns whatever its input is, right? And so what's the return of this entire process EV? Well, if I assign to tap, that returns nothing because it's already assigned the thing off to somewhere, right? So it's going to be a sum type of nothing in the case that it was a local transition, in which case the super machine shouldn't transition, right? I handled the event locally, right? Or it's going to be a transition for the super machine, which needs to just bubble up to it, right? In which case, I don't care about local transitions because my state machine is just going to die anyway because my state machine is in state local storage of a state which the state super machine is going to switch out of anyway, right? So the advantage to this is I don't even have to know the states in the super machine, right? I could say, hey, you are reading something. Well, you know how to read stuff unless you're done, in which case you don't know what to do, or you have an error, in which case you don't know what to do. So this is a template where I can say, hey, this is what to do when you don't know what to do, when you're done, and this is what to do when you have an error, right? So T and U are passed in from the outside and can be anything that fulfills the interface required for, if say this transition is saying, okay, it's an error. Well, here's the step that the error occurred at. Well, then T is going to have a constructor that'll take a step, right? But as long as it fulfills that interface, I can like arbitrarily nest and compose state machines, right? Which is good because I want to model all of my state as state local storage, except for maybe burst events, but that's another topic, right? But you know, I want to model all my state as state local storage, and so I need to just my entire thing needs to be one giant composition of state machines, right? And with this, I can do it somewhat intuitively. So can I actually do this now? Well, yeah, that's kind of starting to work, right? And so if I want to write my entire program in this DSL, then at a high level, I can see where data flow is going, right? So I have this serial port, we call them UARTs for some reason, which is this, this is last year's talk, mix-ins. I'm composing, some hardware driver with some initialization policy with blah-diddy-blah-diddy-blah, and one thing in this composition of mix-ins is, hey, this is the thing you do when you get input, right? Just pass it to this thing, right? And that thing is a, MQTT state machine, which takes in its constructor its submachine of what to do with payload data, because MQTT just knows how to figure out what payload data is, but not what to do with it, right? And then this submachine within MQTT is some, JSON packet parser, which is going to be some, voodoo magic, which Hannah probably is going to write half of, or has already written half of. I just don't understand it yet. To do like text parsing, and then whenever I'm in actual value fields that I'm expecting, like I have this template of, this is the JSON packet that I consume, and here's where the data is, and this is where it needs to go, and blah, blah, blah. I probably defined that earlier, and I'm just putting it in here, right? And then, so those JSON packets will parse out data, and that data is just going to go into the queue, right? Because that we're piping the output of that composed state machine, right? Like the JSON packet events, those things are not going to be any state anywhere in the machine, so it's just going to bubble all the way up to top level and then go through the pipe into the queue, right? And then I have this framework, which is all implemented in the run macro, right? Which has a concept of a queue and has initialization of all the peripherals, and how that works is tomorrow's talk, right? And we have this domain-specific language of how to model interactions with hardware registers on microcontrollers, right? So I can do like super optimized initialization stuff. And this is like almost all of the business logic of my smart light bulb, right? And so like the part of the code that the physicists and the EEs have to understand is massively shrunk and doesn't have virtual functions in it. It doesn't have it is like another DSL that they need to learn, right? But it's a relatively small subset of C++, and they don't have to learn about things like atomic queues, because the queue just is atomic, right? They don't have to learn about interrupt service routines, because that's all handled under the hood, right? And you can't actually your chain of things lives in some driver, and the only way to get stuff out is to put it in the queue and then pull it out of the queue somewhere else, right? So race conditions between interrupts and main thread are very hard to do all of a sudden, because that data is going into a queue, which is atomic, and so it's hard to share, right? And I can see where, and it's very easy to refactor. Maybe I say, okay, well, this UART interrupt is taking too long, right? Because I'm parsing all this JSON and doing all this crap. Why don't I just pipe directly into the queue there, pull them out of the queue down there, and do the parsing there? Well, I can refactor that in, several keystrokes, whereas otherwise that's like a week, right? I mean, you actually go through all the crap, and then you've created bugs, and right? So, yes, Peter.
Question. You said run is macro. I just wondering where that handle event thing goes into within the bottom line.
Okay.
Is it name or typo, or is it magic?
Oh yes, main loop should be handle event. I'm sorry. So this should be going here. I just named, yeah, thank you. Last slide, I almost got through, right? So, so this talk kind of, I'm trying to say things on many levels, right? I'm trying to say, okay, I'm like a fusion metacoding badass, but more importantly, I'm solving my problems in sort of a declarative way, and I think we can fundamentally change the way we write code for microcontrollers. But I mean, for other domains, I don't know how well this applies, right? I don't, that use thing with all the names, I don't know if that maps well enough to like Haskell do notation to satisfy Haskell people. The first couple of tutorial examples seem to map somewhat well with a little noise, right? I know there are people that are like afraid of people putting Haskell in C++, right? And that's why I made sure and not say monad in this talk, right? But I mean, with this optional proposal, for example, by Simon, we have one form of monads as an extension to one kind of sum type, right? And so if we keep going down that route, we're going to end up with like 5 subsets of Haskell in C++, right? And sort of the solution of, just jamming this into the ranges DSL, like I personally think that this probably lowers the intellectual overhead of learning all this functional stuff and whatever. I'm probably wrong, right? Like I'm not an expert on any of this. The thing I'm convinced of though, where I don't think I'm wrong, is that we should be thinking about extending C++ in this sort of style, right? Let's unify giant blocks of things and make sure they work together, which is, I've been reading Design and Evolution of C++. This seems to be what this whole book is about, right? Like, okay, we didn't want to just do sort of cargo culty, let's pull this feature in from this other language and not worry about how it composes with other things and how it works with other things. Let's pull in all sorts of things that work in sort of this grand strategy. And it's obviously clear why this seems like it could be improved in the current standard committee, because there's just so much stuff that doesn't fit in anyone's head, and we're all doing this on our spare time, and me less than anyone else, right? So, but I mean, I hope we come up with sort of synergetic giant things rather than iterative piecemeal things. So yeah, questions? Yes?
So I like everything about this talk except for the unwrap operation. It does look like you're kind of, I don't want to say rediscovering, but working through a lot of the same things that the executors group with Eric and Kirshuk and Jared Hoberuck have been learning over the past year.
Yeah.
And the one piece that's missing is that return values are a very constrained way to express output. And because you wanted to have return values, that's how you ended up with this unwrap operator, which then propagated through. And you figured out at the end of your talk that you actually didn't want that, right? Because you had assigned to as your actual output, which is less constraining. And there are a lot of other things that are less constraining. For instance, if you need your inputs to be distributed over time, then your outputs can be distributed over time, and you can express your output. And there's the fact that things compose a little bit better, because now every output, every pipe is dealing with like something that's potentially an output, right? So there's better composition in that respect also. There's self-similarity. So everything in this talk is like the same things we've been talking about for the past year, except for your unwrapping.
Okay, well,
So really cool.
thanks.
I don't take that as a criticism. That's
yeah, no. That's exactly what I wanted. And like I've said, I'm probably wrong, right? Because I'm not an expert on any of this. As you stated, right? But the design decision behind the unwrapping was to disambiguate in visitation between I want to visit on this or I want to pass this thing that can be unwrapped to the destination, but more importantly, to allow me to compose just regular functions, right? Like, if I say, okay, the things that I can compose are not functions, they're something special, where I'm like secretly passing in the next thing to do, right? then I can chain them without using a return path. But if I want them to actually be able to be functions as well, right, just normal functions, then I need some way of getting out multiple objects out of that function call, right?
Well, if you return via a parameter, then you essentially have that, right? You have void and you return via a parameter, you essentially have that.
Oh, you mean like pass in a reference, which is the return?
Not a reference necessarily.
Or something, yes,
Right?
yeah.
A thing that meets the concept of an output thing.
Yeah, but then people have to change the way they're writing functions, right? I can't say there's all these existing functions out there that I just happen to be able to use. Because, I mean, one thing that I forgot to mention that I wanted to mention, you can't just unwrap tuples. You can unwrap anything that's a product type, right? So, you know, anything where structured bindings work, which is a lot of things anymore, you can unwrap that, right? So the attempt was to be compatible with as much code as already exists as possible, which may be the wrong design decision, right? I'm not, yeah.
Well, I think we're in agreement there. I think there's probably details on both sides of that you're absolutely right about.
Yeah, thanks. Michael.
For what it's worth, we have something similar in BoostStash with an unwrapped thing, so we can just use normal functions and integrate with people's code as it exists today without having to have everybody change their signature. So we found this to be a super useful thing. Anything that comes in that has this concept of, same concept you used, being able to be unwrapped sometimes.
I should have read
It
up
just
on
works.
BoostStash.
You should get a t-shirt.
I think that was the year before I came, the first year.
That's too bad.
Sorry, in the back, I've been ignoring you, sorry.
No, it's okay. I'm newer to C++ now, and so you alluded to, you know, making the people that want Haskell or some sort of DSL ranges as in C++, like making them happy. Is there a history of people wanting this kind of DSL in the language, or like, I'm not sure if you have the answer, if someone in the room has the answer, like, is there a history of this, and this is just now coming to fruition with like C++ 17/20 and optional and ranges?
The question is if there's a history of wanting, you know, Haskell subsets or functional programming in C++. I hope that was a good rephrasing of your question, but yeah, I believe it goes back pretty far. Like there was even a proposal for monadic futures, right? Like a you know, future.then thingy where you could unwrap them and chain them and whatever. Yeah, I mean, there's books on like functional programming in C++, which are quite old. I mean, this is only my third year here, right? So I don't know if this goes back forever, but yeah, I mean, I think there is a group within the community, the people that are doing the, you know, Haskell-shaped cocaine. They really want this, right? And I can very much understand, right? There's a lot of things that is very easy to express in Haskell that is very hard to express in C++.
Do you know who, or can you name those individuals so I can speak to them and join the cocaine group? Eric Niebler.
Eric Niebler. You may have outed him. I mean, your ranges is kind of like a secret Trojan horse to get this all in. Anyway. But man, I'm bad with names. Ivan Kucic? Kucic, something? I'm sorry.
He was the one that authored the functional programming.
Yeah. Or the author of the monadic features. I should know his name.
Were you at the lightning talks last night?
Yes.
Yeah,
I saw your Haskell skills. Yes.
Incredibly.
Like what you showed there at the lightning talk is about the extent of my Haskell experience. So full disclosure.
CPP crowd is another group that's very much functional programming crack doers.
I mean, it's not necessarily just functional programming, right? It's declarative paradigms, it's generative paradigms. There's a lot of paradigms that need to go into C++ because it is the multi-paradigm language. We just have to do it right, right? Yes.
Yeah, I mean, I feel like what everyone else is saying, right? I mean, it seems like it's a relatively contemporary movement to, like, you know, the world is moving on and saying we need to make things more declarative, more expressive, and that's basically anybody who's been yelling for functional features in, you know, C++. That's been this is why. And it's sort of taken a while. People go, no, like functional languages are magic and they work if you don't need performance. But I'm smart. I need to tell, I need imperative features in order to say what I need to do. And I guess compilers have gotten clever enough now that people are starting to trust that the compiler can do the right thing.
Yeah, I mean, there's a lot of optimization potential in here, even in library space, right? And there is, this is also something I'm talking about tomorrow's talk, like, expressing yourself through intermediate code to an optimizer is lossy, right? It's certainly lossy in intent, right? And so, I mean, Hannah's keynote, she's simplifying DFAs in library space because, I mean, the optimizer, there's probably enough information there that it could prove if it had any clue that that's what she was wanting to do in that giant bunch of AST. But you're losing so much intent that we just don't have, even with infinite performance, be able to optimize everything. I think Alistair and then.
I was going to say, the art of a multi-paradigm language is making sure that the paradigms all interoperate well in that language. And this being built as a library on top of C++ moves towards that. And then if these paradigms take off, you get language support because people do creative things in libraries.
Yeah.
But it seems the right way to bring ideas forward.
Yeah, I mean, that's kind of the strategy. Like, I can implement this in C++ 14, just not always const expiry, right? But maybe I don't need that because I'm doing so much in the type domain already. I probably won't get around to implementing this very soon because my kids are consuming all of my time, and the rest of my time is consumed by my company. So, I think it's good to experiment. I mean, that's another thing. We don't experiment in library space enough anymore, right? I mean, it seems like everybody's trying to go straight to committee, whereas we can learn a lot of stuff, and it's a lot more work, but the chances of being right in the end are also higher, right? Marshall.
So I have two things. One that's in response to you was come to my talk on Thursday where I rant about that.
Yes! Somebody smarter than me with a better reputation is going to rant on this. Yes!
We'll arm wrestle for smarter than. But the other one is, I didn't see who said the comment about trusting compilers more. I really disagree about that. What has happened actually in the last few years, and Godbolt is merely the most visible thing about that, is that people are more willing to examine the output of compilers and determine that, yes, in fact, they do what you want, or no, they don't, and make decisions based on that, instead of just saying, oh yeah, the compiler isn't going to do it, or the compiler is going to do it. Now people look. It goes. It's not even trust but verify. It's just verify. Make sure.
Sure. I mean, like people have always looked, but yes, like this has always been the case. Like people will, when things like this come out, they're dubious, as they should be. They check it, and at some point they learn to trust it, and they roll it out. But again, like that's a lot easier to do when like the thing you're trying to play with is expressive. You can go, I wonder. I have a small snippet. If I turn this knob, how does that affect the assembly? Instead of, I have 100 lines because I am the smartest person out there. Oh, let me see, and I change this if, and blows up.
Come to Denver. I have a talk for CPPCon that does a lot of this.
Another thing that I wanted to say and forgot to say in the talk, which you guys are reminding me of, is because this, most of the work is happening behind the scenes where you can't see it, right? I mean, you express an AST, you have a interface to put things into this world, and you have sort of decaying or explicit ways to take things back out of this world, but what happens in there is all unobservable. And we can do a lot of sort of crazy things to make this work, right? Make this really not observable. We can make like packs or unwrapped sums be have private constructors and be friends of the Haskell monobind operator and that kind of thing, and make them non-copyable, and then have to be a temporary because each of the step in the chain takes them by R-value reference, and all these things, right, to make sure that nobody can see them. Because then, I mean, I can implement this in C++ 14 with the stuff I have in C++ 14, but if in C++ 23 we get all this like reflection voodoo stuff, well, I can just reflect on the AST and then build something that's just going to do that perfectly without instantiating any templates besides the actual public interface AST. Peter, yes?
writing on Twitter about our poser one pipes and filters pattern, and Eric Niebler replied, and I read that to you. Coroutines are good for the push programming model. Reactive streams equal push-based async ranges. We are building it at Facebook, but at the ISO level, we are struck pushing, exclamation mark, the executor's rock up the steep hill.
Yeah, except for there's a typo in there because the coroutines are the pull portion of that. And he does mean that because we've had this discussion quite a few times. The coroutines are the pull counterpart to async ranges push.
Okay.
And actually there's a slide about this in my talk tomorrow, so yeah, feel free to have that discussion.
You could also put coroutines like in these chains, right? As long as you yield a nothing or something interesting that just then goes down the chain, right? Then, yeah. Yeah.
This might be a dumb observation, but I'm going to try it anyway.
Okay.
You said you pulled a lot of tricks here.
Yes.
And said, okay, ranges don't do it for me, so I'm going to do something else.
Yes.
But in the end, you have a callable thing.
Yeah.
And you're putting something in there. Parameter
Yes.
pack, whatever.
Yes.
So how is that any different from just constructing a series of ranges, continuations, whatever, and then putting something in there, pushing something in there? Well, in the end, you're pushing something in there.
Well,
Ranges are homogeneous, right?
yeah. Ranges are not heterogeneous, right? So I can't push a pack of different kinds of things, right? I could make like a range of variants and then rely on the optimizer to like figure it all out, right? But also, like, what is the syntax for me to push into a range and then it like go different places in sort of a forky kind of a way? Right?
Senders and receivers.
Senders and receivers?
Yes.
Okay, I really need to read up on this. This is a giant like lack of knowledge. And
It's a
yeah.
moving target. You should probably wait until it's done.
It's not so much a moving target insofar as it's very similar to what he's talking about here. It's just the one piece that's missing is that outputting via return value is pretty restrictive in time distributed domains.
All I'm saying is Dust hasn't settled on what we're going to do about this in the same library.
That's fair.
Well, my comment was more on, you hammered on the push-pull model.
Yes.
And in the end, you're pushing something in.
Yes. Yes. Whereas.
So how's this?
Well, I would argue that interfacing with a composition of ranges, which I may be wrong about, I interact with them in sort of a pull context, right? If I'm a for loop iterating over this range, well, I'm pulling things out of it rather than pushing things into it, right? So ranges. Yeah, I mean, if I'm an interrupt service routine and I just have this byte or message or whatever, then I would like to say, hey, state machine, or hey, like modifier or thing I don't know what you are. Here's a byte, do something with it. And that might be a long chain of things that keep, iteratively doing things with it and swallowing like most of the bytes and then pushing it further in larger chunks and maybe taking that chunk and then, for example, in ranges like, okay, I take a chunk which contains a bunch of bytes and downstream I want to take like one operation that yielded a chunk and then turn it into like 20 pushes because there are 20 things in there, right? I don't really know how to do that in ranges, which might just be by lack of knowledge of ranges. But I mean, I think I could I think I know sort of how to do it in like closure transducers, but not in ranges. Yes?
This looks all to me like it's very much focused on single things. So my question would be if you have made a chain of like a couple of operations and you have like a buffer that is like 1 million or something, you want just do the first operation on everything in there and then like second operation on everything.
Yeah.
Do you have some sort of concept for that?
I'm just going to defer the question.
So that's exactly another point where outputting via return value is too restrictive, right? Yeah. Because outputting via return value you can only do once. But if you have a stream of things coming through, you need to stream the things into some output. And that may be varying across different types. It may be varying across time domain. It may be varying across an index domain in linear algebra.
Couldn't you have an object, a stateful object in this pipe that it gets pushed in a single byte and it buffers up, and then it puts it into the buffer and then returns like null opt or something?
But it can't be returning that multiple times, though. That's a good
Yeah.
point. Like, I could make like special things that go into this composition that can like push multiple times because they know where the rest of it is, like the rest of the chain is. But if I'm a normal function communicating with this chain via my return, I can't take one input and turn it into many outputs, like many outputs after each other, right?
Yeah, so you could buffer, but you can't break
Yeah.
the buffer up into
Yeah.
Just to complete that, if you read the Python filters pattern, you will see that if you want asynchronous or concurrent running filters, you have to do some buffering in between.
Yeah.
That's more or less what your case calls out for, because you want the first result before all the 3 million elements are processed by the first stage in the pipeline.
I mean, for example, if I say an image, it has like lots of pixels, and I want to apply some operations on every of them, generate a new image.
The thing is, if you want to see that image as one thing, which would just work because you pass it down the call chain or whatever you generate from that. But if you want to have, let's say, slice it in tiles and want to process the first tile and want the result for the first tile while you're still processing all the other tiles, and you need some kind of flexibility in the timing of when operations actually work. Even if you have enough cores to make that, you have to have some kind of queuing or buffering in between to get things like that.
I mean, this is very probably like an unconscious bias in my decision making, is that I want as few queues as possible and as few dynamic anything as possible as far as memory management, because I have to be really, really deterministic, right? So if I do two things one after another, if there's an allocate in there, those are going to take different amounts of time, and then I can't test whether I'm breaking real-time requirements or blah, 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 right?
Your domain buffering doesn't make sense.
Yes. So I probably unconsciously biased against like large-scale buffering kind of stuff, yeah.
But buffering is just an algorithm that you stick into that pipeline, right?
Yeah.
You can go from something that is unbuffered to something that's buffered. That's just an algorithm. It's a completely separable piece. It works on any stream of anything, right?
Yeah, I mean, if you look at all of the metaprogramming algorithms, right? They are aware that they are part of an AST chain, right? And so they could like push multiple into the down the chain while having one thing pushed into them and then pushing multiple down the chain. And obviously you can always buffer, but the sort of the normal function calls which you put in there, which we need unwrapped to be able to support, well, they obviously can't, right? Yeah, in the back. Yeah.
I'm stretching.
Yeah. Okay. Yeah.
So yeah, I mean I think the issue that we're encountering, because just to put more words that people hate, I mean, because you had two combinators there, right? You had let me do the pipe and let me have the operator fish.
Yeah.
And yeah, it's reasonable that those two combinators, they're for, one says pass along this blob, one says unwrap it and pass it along. So yeah, those aren't going to fit the use case of I want to aggregate that. But the solution isn't necessarily like that doesn't preclude you from being able to lift functions, which is what you're saying.
Yeah.
With return values, you can do what you can't do if you do with a parameter. You just
I mean, I don't think these can't coexist in the same DSL, right?
Exactly.
Yes.
There's algebra.
One solution would maybe be to have unwrap for a sequence be to push all of the things out of it. So the function returns itself a lazy sequence.
Yeah.
And then it concatenates it down.
Yeah.
Unwrapped is just a higher order function, right?
Yeah.
That you apply to some algorithm that either you need the thing unwrapped or you need the thing not unwrapped.
Yeah. I mean, in most cases, I'm just taking the same type and just saying, hey, here's a tag. This is unwrapped now, right? Like under the hood. Another thing that I've been playing around with is like a lot of the time you're going to have like this queue of events. You're going to want to like peek and poke or whatever it's called. Like you want to go through the queue and find this kind of event next and whatever. And you can actually also pretty ergonomically express that as filtering the queue, right? I'm going to filter the queue and then pop. And okay, well, I got a nothing, so let's go down to the next priority, filter on that priority, and then pop. Oh, I got something, let's keep popping, right? I think we're pretty much done, so thanks, everyone.